So this is an introduction, video introduction to some code that I wrote on GitHub. So basically, what I'm going to do is I'm going to go over a number of topics in a series of videos. So, and then when at the end of these videos, I'm basically going to go ahead and show what I did with the code and how this code, if I can get it to run, how I'm able to get this code to function in order to do a simulation of the Navier Stokes equation. So the Navier Stokes equation is basically a fluid simulation equation. So it's a very common way of doing numeric fluid computations. And so basically what this equation does is it creates a grid with squares with individual velocities, and then it goes ahead and computes how the fluid moves in response to various factors like force. And running the simulation can get various interesting quantities out of it. One of the most important, which is used in modeling aircraft, is the pressure field. So this is a very common equation used for computational fluid dynamics, predominantly for things like aircraft design, automobile design, and that type of stuff. And I basically wrote this program, which is available on GitHub, that does this modeling, where it basically generates vortexes. And what this program was predominantly based on was basically this chapter in GPUGems that is available on the Nvidia Dev site. However, this is a somewhat older book, so when they did this chapter here, they are not using CUDA, so I basically wrote this up so that it actually uses CUDA, which is the more modern method for actually going ahead and doing computations on the GPU. So see if I can show some CUDA, actual CUDA code in here. Yeah, so this is basically the CUDA stuff. A very simple implementation of CUDA, probably not the most efficient, however, it does at least work. And it uses the graphics code, so it's much faster than running this would be on a GPU. So to begin with, I'll go over some of the sources. So this is actually the book, one of the series of books that I learned calculus from, actually going through high school. And then this is a book from my undergraduate that they taught multiple variable calculus for 18022 for MIT back in the early 2000s. So this course is basically, most of my videos will assume a working knowledge of multivariable calculus, so vectors, curls, all that kind of thing is advisable. My sources, I started out with GPUGems, where they have variants on the derivation of the Navier Stokes and Hill, and then went through a number of other sources online. One of the best I've been able to find is this guy, which is basically another MIT open courseware course. It was originally 1801, which is the basic physics for MIT, and apparently spring of 2022. Then, in addition, there's a number of other support documents that are optional. This is the document for going through the Leibniz Rule. And this is for basically the computation of the matrices that will be used later on that actually solves the Poisson equation. And this is, I think, another matrix equation. And then this is the multi-grid, because this is basically another variant on solving the Poisson, but this is a way of accelerating the solution to the Poisson equation. And then, of course, this is my own code. So, I'm going to switch over here. So what will be covered in these videos, I'm going to start out with a derivation of the Navier Stokes Equation. And basically that comes from breaking the fluid. So there's this area of the fluid flow, basically breaking it up into discrete cells. And then applying essentially force equals mass times acceleration. And that ends up with this very long equation, which I will go over in much greater detail, which is basically the velocity mass. So that's basically the mass for acceleration term, including the d by dt. So that side. This is actually written backwards, and then this is the force side. Then I also have an optional part, which is the proof of the Leibniz Rule, which is necessary to solve derivatives like this one, where the integrand actually is dependent on the time. Then after that, goes through the derivation of the Euler equations, which are basically a predecessor of Navier Stokes. So these end up with an equation that looks like this after this derivative is worked out. And that's basically the straight acceleration. And then I think that's the advection. And then this is basically, G is basically a force, gravity, and then the pressure. Then I'll go over the physical implications of the terms in the Euler equation, so what each of these terms actually relates to, as opposed to how it actually affects the motion of the fluid, and how the pressure basically turns the fluid into a fluid, which is actually interesting. And then go through an optional term is to go through the viscous stress tensor as a prelude to converting the Euler to the Navier Stokes. Involves adding viscosity, and most of the viscous stress tensor appears to be straightforward. However, there are strange terms in it that if anybody who's actually tried to solve this should have come across this duy dx term, where it does not appear that it should show up. There should only be a dux dy up in the trivial sense. So I'll go into how that term actually arises. And it actually comes out from the viscosity, not the viscosity, it actually comes out from the fluid rotation. So this is actually a vortexity, can't say that, but it's basically a vortex term. So this is actually covered at the beginning of this document. It actually goes over how that term actually comes out. It should show up right about there. So to go back to the introduction, and then I'll go from, after coming up with the viscous stress tensor, then I'll go from the Euler to the Navier Stokes by adding the viscosity. So I finally end up with this entire term. Well, this is the viscosity term. Okay. So that pretty much finished the derivation, the mathematical derivation of the Navier Stokes. But after that, the next thing to do is to convert the Navier Stokes equation into a format that can be solved numerically. So I have a short optional section on finite difference methods, which is basically how to differentiate on a grid. And then I'll go into computing the force and the pressure, then adding the advection and viscosity. And then I have a very long optional section on how the Poisson equation is actually solved using Jacobi iteration, which basically ends up turning it into a problem in matrix or sparse matrix multiplication. So I'll go over the convergence of the single variable Jacobi, and then the convergence of the two variable Jacobi. And then finally, since it turns out that the Jacobi actually does not converge very fast, even at a grid of only 64 by 64, it was actually necessary to use a multi-grid method. So I'll go briefly over that. And then I'll go back to my CUDA code on GitHub and describe exactly what I'm doing with that. And then finally, I'll go through the program output, which is what I was showing in Windows, and basically demonstrate how this actually does in fact relate to real physics, and that these things do actually look like real vortexes. These things are being basically generated by a force field that's spawning around where I initially click with the mouse. So as I go ahead and it's basically in a Gaussian shape, and it has a force in the direction that I drag the mouse. So what that actually does is it creates these little vortexes, which then spin around and move the die. So I'll go through the program, and also some Python code that I used to visualize this. And then finally, I'll go through the Nvidia Dev GPUGems book and go over a few things that they didn't completely get right with that calculation. His pressure calculation is a little off, actually, which improves his convergence considerably, but it probably does not lead to accurate results. So that's it for the intro, and the videos will be being posted shortly.